The past decade has seen the proliferation of embedded processors into all kinds of objects with no business being smart. From toasters to toothbrushes to light bulbs, it would seem that everything nowadays comes with Wi Fi and Bluetooth, and it integrates with your cell phone through one of a thousand poorly designed apps. So imagine my dismay when redoing our kitchen to find that the cabinets, counters, and backsplash were just dumb chunks of wood, granite, and glass. Something had to be done, so I took matters into my own hands and I built this, the Backsplash LED display. No longer is the backsplash just a water-resistant, easy-to-clean surface. Oh no, now it's a full-color display. It can give you a light show, display the weather, be a nightlight, can even display images so that I can rickroll my friends while they wash their hands. I do, admittedly, still need to write most of the code for this. Now you've no doubt noticed that this isn't really a backsplash so much as it's 32 tiles in the middle of a wall. And that's because this takes a tremendous amount of time to implement. So you'll have to bear with me. This will one day be covered in tiles, but today I'm going to show you how I got these 32 built and installed, the challenges I encountered, and the solutions I dreamt up. We better get into it. This project all started when we decided to install these small glass hexagon tiles as our kitchen bar backsplash. Since they're transparent glass, I had the idea to add an addressable LED to each one so they could be individually lit. There are around 300 of these, so if you step back, this becomes a sort of display, with each tile being a pixel. It has been quite a process getting this implemented. Each pair of tiles gets a flexible circuit board with two 1.4mm RGB LEDs on it, on these little prongs. These get bent at 90 degrees and go between the tiles, facing opposite directions. Each of these boards also has two microphones. These microphones get coupled to each tile so that they're excited when a tile is touched, making this not just a full-color display, but a touchscreen. Finally, there's the electronics to make this happen. A 10-cent Poya PY32 microcontroller and a dual op-amp for the microphones. All this gets crammed onto the small board and duplicated over and over again for each pair of tiles. I'm not going to get deep into how the circuit or the software works in this video, but I have done that in previous videos. So if you're curious how the LEDs work, or maybe if the 10-cent PY32 microcontroller is a good fit for you, or how I'm using the signal to the LEDs to time the microcontroller's response to the main processor, well then you should go check out those old videos. There is tons of detail there, probably too much. And you know what? You should like and subscribe because there's a lot more projects like this to come. I started this project around 9 months ago by building the original circuit boards. I tested them on a couple tiles, immediately found improvements, and I respun the boards. I got these new boards in, tested them, did a little software development, and I again changed the board. I received the third iteration, this one, tested them, and you'll never guess, I made another revision. Since I need to make a couple hundred of these, I'm being particularly cautious to make sure everything is correct, as I don't want to have to bodge a fix on hundreds of boards. But they're here. This is the Rev D board, and this one is perfect. Or at least it better be, because I ordered 350 of them to complete this project. Now I've obviously already made several prototypes, and this board redesign is a minor revision of the last, so I'm jumping right in by making a bunch of these to complete the first full sheet of tile for the backsplash, which is 16 tiles. The first thing to do is populate the boards. I went ahead and ordered a stencil for these boards, and if you followed my channel in the past, you might have seen the solder paste stencil printer I built. I created a new frame for that clamps the stencil rather than epoxying it on, and then I cut this stencil down to the appropriate size and I installed it. Next, I lined everything up, printed the solder paste, and I placed the components. A quick trip into the reflow oven and the backside was done. Now I just flip them over and I repeat those steps for the front side. This did a decent job, but pretty much every one had shorting between 2 or more pins on the PY32 microcontroller. I had to fix this by hand with a soldering iron. A quick wash in isopropyl alcohol, and that finishes the board. By the way, these boards and the stencil came from the sponsor of this video, JLC PCB. JLC PCB is a one-stop shop for all your circuit board needs. From simple 2-layer designs up to 4, 6, 8, 10, and even higher layer counts, JLC PCB offers affordable circuit boards with a wide variety of options. From multiple dielectric types to gold-plated finishes, numerous copper thicknesses to a variety of solder mask colors, and even flexible PCBs. JLC PCB offers it all, unlike other vendors where you're stuck with a rigid set of options. They've got a great online ordering system that will provide you an instant quote, as well as real-time design for manufacturing checks. To top it all off, they offer affordable PCB assembly and have a number of coupons available to save you money on your next project. Check out the links in the description for these great offers. With the boards notionally complete, I did a thorough microscope inspection to look for any soldering defects, and then I went into electric testing. I'm testing these using my automated PCB tester, which I sort of built for this, and you can check it out in my previous video. And I've got to say, this thing is working really, really well, and I cannot imagine doing this project without this. I have done a few improvements to this since my last video, mostly correcting some bugs, but also making it so that messages are displayed on the screen in addition to being written to the SD card. I'm using this to test the board in 3 steps. First, I perform a short circuit test between all 11 pins that this connects to. I also measure the specific resistance between power and ground to verify that it is within an acceptable range. Once I've done this on the whole lot, I run them through a second time, this time using the tester as the programming probe. I'm using the tester in combination with a PC and Keel Microvision to flash code to the onboard PY32 microcontroller. Once they're all programmed, I run them through the tester a third time to check the functionality of the LEDs and the microphones. First, I light the LEDs one at a time, and I use photodiodes in the tester to verify that the LEDs are turning on and off as expected. Next, I use a piezoelectric buzzer in the tester to excite the microphones. I then digitize that value and I send it back to the tester for verification. Finally, I added a step to slowly light the red, green, and blue LEDs, one at a time, so I could visually verify they are working. I 3D printed a new lid to the fixture out of clear polycarbonate so that I could really see what was going on. The tester was very useful, particularly for checking the microphones, since those have proven tricky to solder correctly. On some runs, I've had upwards of 50% of the boards with at least one microphone that didn't work correctly. What seems to be the issue is that the 2 rectangular pads get plenty of solder, but the annular ring around the sound port just doesn't get enough solder to connect. It's a very narrow opening on the stencil, and I think it's just not getting through there consistently. This necessitates me reworking the microphones with a hot air pen, which is annoying but relatively simple. As a random aside, while reworking the microphones, I accidentally delidded one of them. If you're curious what's inside, then here you go. There's the silicon microphone sensing element, the preamplifier, and a capacitor. And this is an 0402 capacitor, just for size reference. With the boards soldered and verified to be functional, they are ready for mounting to the tiles. Now, this is quite a process. There are around 20 steps that need to be completed, all in the right order. It's complicated enough that I made a checklist to verify that I hit each step. Let's go through it really quick. First, I need to prep the tiles. This means removing them from their packaging and ripping the cardboard off. There's usually a ton of glue on one of the tiles that needs to be scraped off, carefully, or I will damage the tile. Then I cut the netting between all the intersections, leaving just a thread or 2 left intact. I find the spacing between the tiles is not consistent from the factory, so cutting the netting allows me to reposition them. Next, I'll snip away the netting between the tiles where an LED board is going to go. Since I'm shining the LEDs into the side of the tiles, I need to verify that the appropriate side is clear and transparent. The back of the tiles is coated with some kind of paint, and overspray will often get onto the sides of the tile, so I use a hobby knife to scrape it away. I will then give it a quick cleaning with some isopropyl alcohol. Once that's done, I insert these custom 3D printed tile spacers between the tiles. I capped on tape them in place to rigidify the sheet. Whew, we're just getting started. Now, I need to mount the circuit boards to rigid frames. Since these are flexible PCBs, the prongs with the LEDs will kind of just go wherever if I don't constrain them. So I've 3D printed these small frames to hold them in the appropriate orientation. I will mix a small amount of this transparent slow-cure epoxy, then I will load it into a syringe and apply a bit to each side of the frame. I place the circuit board on and I clamp them with these 3D printed machinist clamps, which I scaled to be just the right size. Once that's cured, I mix another batch of epoxy and I glue the rest of the board to the frame, holding it in place with capped on as it cures. Now, I'll mix yet another batch of epoxy and glue the PCB and frame to the tile. I apply epoxy to each LED, the frames, and then a big glob on each microphone. Press it into the tile and hold them down with yet more capped on. Once that is set up, I go back in and I inject a fourth application of clear epoxy around the microphones just to make sure they're really well coupled to the tiles. Now, I'll flip the tiles over and inspect the LEDs from the top. If there's a gap between the LED and the tile, I mix and inject a fifth application of clear epoxy so that nothing can get between the LED and the tile. Grout, for instance. Once that is dried, I flip it back over and I cover the sound port hole in the PCB with a small bit of capped on so that nothing can get into the microphones. I mix some black epoxy. I'm using JB Weld plastic epoxy here. And I place that in a thin layer over the side of the LED to minimize light coming out at 90 degrees. I need to be careful here though, to make sure that the epoxy isn't too close to the surface of the tiles, or there won't be anywhere for grout to go. Still not done. I once again flip the tile over, and I solder this 4-conductor ribbon cable between each of the boards, including this long segment that goes diagonally. There's also the input and output wires. I then grab a multimeter and I check for shorts between the wires because I've got way too much work into this assembly at this point to make a stupid mistake like that. Once that's done, I mix the 6th and final batch of clear epoxy and I glue the wires down to the tiles. We're almost done now, so I hook the appropriate wires to a controller board. I'm using an STM32F4 Nucleo in this case, and I do a functional checkout of the assembly. The LEDs are easy to verify, but I will also check the microphones and make sure I'm not getting zero readings from them. Finally, I'll clean the boards up as best I can with a cotton swab and alcohol, and I'll give them a couple coats of acrylic conformal coating, which is some really smelly stuff. I have some slight concerns that something in the grout could cause corrosion on the circuit boards. That's why I'm applying a conformal coating. If we ever sell this house, I want to hand the owners 100 pages of documentation and the code for the backsplash, just to see their expression, so I need it all to be working well into the future. You'll no doubt have noticed that there are 7 epoxy steps in this process. I used to hate dealing with epoxies and adhesives in general, but let me tell you what has really helped my consistency and my enjoyment of the process. First, get dedicated and disposable mixing equipment. I use these 2-ounce medicine cups that you can get from the usual sources like Amazon. I also have a set of stainless steel mixing sticks, which are pretty affordable, and they can be easily cleaned with alcohol. There are disposable options for this as well, if you're so inclined. Next, get some syringes. Seriously, this is one of the best purchases I've made for my shop in the last few years, probably the best dollar for dollar. These are 3 milliliter disposable syringes with lure lock threads on the front. They're dirt cheap, about $15 for 100. Then go out and get assortments of tapered plastic and metal needle tips. All this is going to run you about $50, but it's hugely worth it. If you're like me, you'll find you're particularly fond of a certain size and type of tip. I mostly use these 16-gauge tapered plastic tips, for instance, so after you buy the assortments once, just go out and buy 100 packs of what you use the most. I've included affiliate links for all this stuff in the description, so if you're still mixing epoxy using a popsicle stick and a scrap of cardboard, then go check this stuff out. It'll make adhesives so much more enjoyable, or at least less awful. When I powered up the first set of tiles, I immediately noticed that 2 of the tiles were very dim compared to the rest. these two tiles, which are adjacent but they're not on the same circuit board. I inspected the tiles for clues, and I came to the conclusion that these LEDs were further away from the tile, and therefore there was more epoxy between the LED and the glass, leading to higher light loss. To fix this, I redesigned the board frames with this flexible spring tab on one side. When pressed between the tiles, this tab pushes on the opposite tile, firmly pressing the LED into the glass. I went through a few designs to get a frame that printed correctly and worked well, but I'm pleased with where it ended up. But I don't believe this was actually the issue. While building the next set of tiles, I noticed something peculiar. On some tile edges, there is a silvery gold coating, almost like silver nitrate, although I doubt it's anything that expensive. This seems to be added to make the back bevel reflective, which is great, but sometimes it bleeds onto the side of the tile as well. This coating is quite reflective, bouncing the light back into the LED rather than letting it into the tile. I tried removing this with a knife as well as heat, to no avail. I noticed that it usually only occurs on one or two sides of the hexagon though, so going forward, I will simply rotate the tile to get a clean edge, and then mount the LED to that. I did this on the second sheet of tiles, and I'm very pleased with the result. All 16 tiles are evenly lit. With the entire sheet of tiles built, and numerous checks showing that everything was working correctly, I was ready to install them onto the wall. Now I cannot stress this enough. This is not a video on tiling. If you're looking for advice on installing tiles, you're in the wrong place. If you find my tiling technique egregiously offensive and you have suggestions, feel free to let me know in the comments. Anyway, I mixed up some thinset. Mastic would typically be better for a normal backsplash, but I wanted the thickness of thinset as the wires and boards need to go between the tiles and the wall. I 3D printed this custom comb with 1/4 inch wide and 3/8 inch deep notches to try to get even more thinset back there. This kinda worked, but I might play with a trapezoidal shape in the future. I then marked the center of the wall and carefully measured the heights where each sheet of tile would go. Ordinarily, I would start at the bottom and work up, which makes far more sense, but I wanted the first sheet of tile to be higher up where it's less likely to be touched, just in case the microphone touch sensors don't work on the first attempt. I also plan to have a shelf on this side, so the tiles that are dim won't be as noticeable. I'm just hanging the wires out the side for now, but in the future I will drill them through the wall. This is up against some stairs, so behind this is an opening, which will make a convenient place to hide the wiring and controller. After the thinset dried, I gave the tiles a real quick checkout, and then I installed the second sheet. There's one small issue with how I've got these installed. The LEDs and microphones are addressed sequentially in the order they're connected. So with how I've got this wired, this is number 0, this is number 1, and then 2, 3, 4, 5, 6, 7, and on, down to 16, 17, 18, 19. It's basically just random. If I was to try to program the pixel values directly, it would be a nightmare to figure out what went where. So I've created an array in code that remaps this sequential location to an XY grid location. This of course isn't perfect with hexagonal pixels because adjacent columns move up and down, but I just need to remember that even columns are high and odd columns are low. I'm not going to be running the wall as one continuous string either. If I did that, a single part or connection failure would take down everything after it. Plus, it's a fair bit of current to run through a single 26 gauge wire. Instead, I'll run 6 to 10 independent strings, depending on the number of timers and UART peripherals available on my controller. The remapping function will also take care of this, meaning I can just code it as a grid, and the back end of the software will take care of the rest. As an initial test of the touch sensing, I've implemented code that turns a tile from green to magenta when it is tapped. It basically just looks at the microphone values. If any of them exceed a predefined threshold, it'll find the biggest value and change the color of that tile. As you can probably tell, this doesn't work very well. The reason is that certain microphones, for some reason unknown to me, are much more sensitive than others. If I tap some tiles, you can see that it almost never lights the right one up. For my first attempt at fixing this, I've implemented a calibration technique where I go one by one and tap each tile with a roughly consistent intensity. I then save those values as the baseline. I compare subsequent taps to that baseline, and I calculate the proportional intensity as the percent over the baseline. This works far better, but it's still not perfect. In the future, I'll probably test out a couple other methods. Interpolating a multi-point calibration is one idea, or I could perhaps implement a convolutional filter of some kind. With a couple of sheets up on the wall, I couldn't resist taking a few minutes and coding up a couple different patterns. Flashing through the colors was the first thing I did, as it's very easy and actually quite satisfying. I then implemented this rolling color effect. I'm a little late on this one, but this is a spooky flickering effect that'll be useful for my next Halloween party. Finally, here's a light chasing effect, similar to what you'd see on a marquee or something. With only 32 tiles up, I didn't get to displaying images or text, although I plan to implement that in the future. I want to make a script, probably in Python or MATLAB, that will convert bitmap images into RGB data and will handle the downsampling of an image with rectangular pixels onto a display with hexagonal pixels. Building this has been very time-consuming, but it is coming out really well, so it's on to production. There are 12 or 13 full sheets of tile left, and then I'll need to cut down tiles and fill in all around the edges. When I built the second sheet of tile, I recorded the time it took me to do each step. Populating both sides of 24 tiles took about 6.5 hours. Cleaning a sheet of tiles, mounting the boards, doing the wiring, etc., that took about 4 hours. Doing the math, it takes me a little over 6 hours to do one sheet of 16 tiles, or about 20-30 minutes per tile. I've got my work cut out for me. I'm not going to make any guarantees of when it'll be, but next time you see the wall, it'll be completely tiled. Building this has been a tremendous undertaking, but it's finally coming together, and I'm really pleased with the results. It's not quite as bright as I would like, but it is visible even during the day. I can't wait to get it grouted, because a lot of light is lost through the edges of the tiles, and I'm hoping that a white grout color will reflect most of that light back into the tile, improving the brightness and the consistency. That's all I've got today. I hope you found this interesting, and as always, if you've got questions, comments, or anecdotes, please leave them below, and I'll do my best to respond. Thanks for watching.